Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We have two presenters for this cloud computing for planetary defense. Stephen Johnson and Kenji Takeda. They're from University of Southampton.
So yeah, I just want to acknowledge this is obviously a team effort. So I'm Kenji Takeda, and I'm co-director of the Microsoft Institute for High Performance Computing at Southampton with Simon Cox. Stephen Johnson is our postdoctoral researcher who's done all the hard work. And then Hugh Lewis and Graham Swinard are two of our astronautics faculty members who are the sort of scientists on this project. So apologies for the resolution. The laptop's being a bit funny, so it's a little bit crunchy, but hopefully you can read it. So, like I said, we're from the Microsoft Institute for HPC. It was launched in 2005 by Bill Gates at Supercomputing, and basically we're an engineering department, and we're looking to see where we can use Microsoft tools to try and help with engineering processes. So for the talk, I have a very brief intro on cloud computing and why we're using it in this application. Talk about space situational awareness, which is the NEO asteroid impact scenario, and actually our demo, which is on space debris environment. And then Stephen here is going to run a live Azure demo, which should be fun. And then we'll just conclude at the end. So cloud computing. So obviously, everybody has been talking about cloud computing. When we come up problems and a scientist or engineer comes at us, we don't say, yeah, use the cloud. Or we don't say, yeah, use HPC. We try and understand the problem, and we try and use the most appropriate cost-effective resource that we can. So looking at the cloud, these are some of the characteristics with the cloud. One of the features is it's a pay-per-use system. What that means also is it's scalable. So as we saw in the previous talk, if you've got your workflow, the workflow will scale the computation depending whether you need, in the previous talk, 1 machine, 50 machines, 5,000 machines, 50,000 machines. You can scale out and scale back. What that means is you get burst capability. So, and that's what this application requires. So the fact that I may only need a few computers today, the next week I might need 10,000 computers for an hour, and that burst capability is what's important. And if you have your own facility, and we're lucky enough to have a brand new facility coming online in Southampton, you have significant capital costs. So we have a new 8,000 processor machine at Southampton. It costs about $5 million. You worry about utilization, and if you're not utilizing your machine, the people who've given you the money start asking questions. So cloud is quite nice because it allows you to scale, and you have more of a subscription model. And that's what's quite nice. We hope we have reliability, sustainability, and also the ability to access from anywhere. So at the moment, these are the three main cloud computing offerings. Amazon, I guess, were first to the game. Google were next. And Microsoft bringing up the rear here with Azure. So this is the sort of span. So Amazon basically gives you a box in the cloud. It gives you a VM, and you have to do everything. Okay, so you have to upload your image, build your image, run it, manage it. You have a fixed IP for a machine, although they're fixing that now so you can have flexible IPs. Google's at the other end. Google gives you a Python runtime or a Java runtime. That's it. Don't think you can get a file system. Microsoft's somewhere in the middle where you get an operating system. So you get things like a file system. Now, an analogy to that I like to use is if you're going for some web hosting, you can rent a dedicated box. They give you a box. You load whatever you want on that box. Costs a fair bit of money. You can go to the other end when you say, actually, I just want to run a website. So I want to pay $5 a month, and I want to run a CMS like Drupal, Joomla, and I just want to put some web pages on there. In the middle, you might go to somebody like Rackspace and say, well, actually, I want a server, and I want Windows Server on that, and give me SQL on there and some IIS, but I'm going to load some apps on there too. So it's somewhere in the middle. And obviously, depending what your business is and what you're trying to do, you want to use the most appropriate solution. So that's my 3-minute guide to cloud computing. Space situational awareness is what this application is about. Space situational awareness is really about the area of space around the Earth. It's very important for operating space vehicles, so satellites, launch vehicles, and that sort of thing. What's happening is that every time we launch a vehicle, say a rocket stage separates, you end up with a dead rocket stage. You end up with all the bits, like bolts and things that come off the rocket stage, and a lot of those things stay in orbit. And so we get this debris cloud, basically. It's often called space junk. And what can happen is things can run into other things. In the case of Cosmos and Iridium, two satellites can hit each other. And that's obviously very bad, and it also creates more debris. So the subsequence of that is that, for instance, on the space shuttle on the recent Hubble mission, there was a 1 in 89% chance of an astronaut actually being killed, and a 1 in 229 chance of the space shuttle being hit. The space shuttle has had to replace 92 windows because of space debris. That's usually due to something like a paint fleck the size of my fingernail hitting at 17,000 miles an hour. It's a lot of kinetic energy, and so debris is a big problem. However, it's not nearly as big a problem as an asteroid hitting the Earth, because it could be the end of us all. We all went to the Carnegie Museum and we saw the dinosaurs there. That could be us, okay? So that is another issue. Space situational awareness also covers space weather, so things like solar activity that can knock out satellites and things. So so in order to manage this, okay, we need to observe. So we need to look and see what's out in space, and we need to observe the satellites, look at NEOs, find out where they are. That generates a lot of data. From that data, we might want to do some modeling and prediction, and from that prediction, we might want to take some action. So in the case of space debris, for instance, we may spot a piece of debris, and we may need to move the International Space Station out of the way. And they do that on a regular basis. It's an international problem because space is an international issue for everybody. And actually, this work at Southampton, we helped to inform the United Nations Committee on Peaceful Use of Space. And actually, the space debris modeling that you'll see is used to help form UN policy on space debris and space debris mitigation, and also licensing of satellites. So when you actually want to launch a satellite, we have to do some analysis to make sure you're putting it into an orbital slot that doesn't interfere with other satellites. So the work you're seeing here is actually involved in that. So planetary defense is important. So the space situational awareness issue is quite big. And people are concerned with this. So the US is spending $9 billion over the next 5 years on this space situational awareness. The Europe is spending several billion euros on space situational awareness. So this is a tricky one. So asteroids. So there are thousands of asteroids spinning around the solar system. If an asteroid bigger than a kilometer across hits the Earth, we're all dead, basically. It's what we call a civilization killer. And the odds of that happening hopefully are quite small. But if it did happen, it's going to be bad. But like I said, the odds of that happening are quite small. There is this thing called the Torino scale on the right, which is a scale of severity. The civilization killers are basically 8, 9, or 10 in its combination of probability of hitting and also the size of the impact. What's of a greater concern are the smaller asteroids, because these things are quite hard to spot. So the US government has tasked NASA with tracking every kilometer-sized asteroid. It's actually in Congress. They passed a bill, and they ring-fenced some money so that NASA had to do that. And they're pretty much on the way there. So that's the big stuff. The small stuff, however, is quite dangerous. So in 1908, an asteroid didn't actually impact. It was an airburst over Siberia. And that had a power of about 15 megatons, okay? And it flattened an area the size of London, okay? These things have a higher probability of hitting the Earth, about 1 in 10 chance of that happening in this century, okay? So these are the things that we're really worrying about now, because when these things come past, sometimes we don't see them until they've already gone past the Earth. So that means that one day maybe one might not get past the Earth and actually hit the Earth. So these are the ones that we're actually very worried about. There is one particular asteroid called Apophis, which is suitably named, which is about 270 meters across. In 2029, it will pass within our ring of geostationary satellites. Okay, that's quite scary. You'll be able to see it in daylight. Okay, and hopefully if it's not getting any bigger, that's good. If that were to impact, and it is due, there was a scare in 2004 when we were observing this, and the odds of it impacting went up to 1 in 37. That went to number 4 on the scale there on the right. Subsequently, as the observations started coming in and the calculations were refined, that probability reduced, which was good. And at the moment, in fact, about 10 days ago, they announced a revised estimate, which means it's 1 in 25,000. That's based on observations from telescopes, and there's an opportunity in 2013 when it does a close approach that we can put something on the asteroid so we can know exactly where it is, because if it were to impact, this is when it would impact, put it in your diaries, and it would impact with the equivalent of 880 megatons. That's 4 times the power of the Krakatoa volcano, which had a very significant effect on global climate. We essentially had a nuclear winter. So this is a problem, and so we are involved in trying to do some modeling around this. This is something that happened quite recently. Something hit Jupiter, and there's the scar. That scar is the size of the Earth. Okay, so there are asteroids, and we didn't see this one coming. We're not really, but you know, it happened and took everyone by surprise. So it's a little bit scary. What we're going to talk about today, actually, is the space debris aspect. So this is one of our models, and it's in fact the model that we've deployed in Azure, which allows us to track satellites. And this is a modeling we did of the Iridium Cosmos satellite collision. And you can see how, you know, we've got the orbits, and then we see what happens in the middle when they collide, and then subsequently what happens. So this is actually what we're going to do a demo about today. And like I said, there are a lot of fragments out there, and this is becoming an increasing problem. There are about 10,000 objects in orbit that are quite big. There are about 300,000 objects that are about the size of the fingernail sort of thing that hit the space shuttle, and we want to be able to track those and model those. In order to track them, we have telescopes. So there are some proposed new European telescopes. Europe's spending about $1 billion on these new telescopes because this affects our space infrastructure, communications, observation, and military. And so this is the sort of global network of sensors. And what we need to do is, if we want to try and tackle these, this debris issue, we need to track all these objects. And we need to share the information about those objects. Because if you're a Russian satellite operator and an American satellite's going to hit you, you kind of need to know, you might want to talk to each other. So the problem is that people don't always like to reveal their sensors. If you're the US military and you have a very good sensor, you might not want somebody else to know that that sensor exists. Okay, so the anonymity of where some data comes from is quite important for a lot of users and suppliers of information. So Richard Tremaine Smith, who's one of the people who runs this activity at the British National Space Centre, or recently retired, said these few things. And one of the things he says was, well, why don't we put a software application between the really sensitive data and the sensor data and the end users? And so we thought, hey, that's a good idea. So we've come up with this idea, which is a service bus for space situational awareness, which in our case sits in Azure. And that is able to consume information, ground observations, space observations, and in the cloud we can distribute that information, but we can sanitize it, okay, and we can have a scale of fidelity depending on access control, and then we can actually have simulation tools in the cloud, which is what we're going to show now, and then the results from those can be used by decision makers and satellite operators, and in the case of the NEO impacts, decision makers, emergency authorities, in order to plan for that. So this idea of a global computing platform to help everybody, because it's an international problem, everybody has a stake in this, is what we're going to show off. And I shall hand over to Steve, who's going to do the demo. There you go, Steve.
Okay, right. Thanks a lot, Kenji. So what I'm going to show you today is an Azure demo that we've got. Just to give you a brief overview of the features of Azure that we're using. It was briefly mentioned earlier on today, there are 2 types of worker roles. Well, there's a web role and a worker role in Azure. The web role has access to IIS, but essentially they're just units of processing. So we're using both web and worker roles. we're using the Azure tables. Now, an Azure table's slightly different. It's not like a SQL table. You can't join them. It's not transactional to some extent. And but the point is that it's super scalable. So you should be able to scale up to many millions and millions of rows. To index a row in a table, it's indexed by a partition key and then a row key. We're storing data, the binary data, in blobs. This is Azure blobs. And also I'm taking advantage of the local storage, which is not persistent, but every worker has a disk that you can write some scratch space to, basically. One of the key features of cloud computing is that you want to be able to make it to scale very well, and so you need to have some way of allocating work to these worker roles. To do this, we're using data-driven queues, and so every worker comes along and picks off the next piece of work from the queue. We're also using relational databases. So this is SQL Azure, which was released about 3 weeks ago, and I've actually ported this to the SQL Azure production hardware now, which was released 2 days ago. So it's quite exciting that that's all up and running now. And I'm going to show you a little front end that we've put together using Virtual Earth and XBAP and WPF, and I'll talk about that in a minute. So how does it all work? Now imagine if you were like a satellite owner. You basically want to get a text message that says, my satellite is going to collide with something. How do you get this information? Well, SpaceTrack actually publish a list of about 10,000 objects. That's debris and satellites. They publish it twice a day. There are other sources. There are amateur astronomers which publish TLEs. So the first stage is I've got an importer, a worker process that goes along, and you can harvest TLEs. Now, TLE is a 2-line element. There are actually 3 lines in it, which is good because the acronym still works. A TLE is basically the position. It's an orbit of it's the orbit that the piece of that the object is taking at that current point in time. A TLE is a standard format. It's used by many applications. So the first stage is to import these TLEs and to store them as Azure blobs. I'm not doing any processing on them. There's just this worker that goes along and harvests them. And the point I'd like to make out here is that this middle box is each one of these, it's going to appear as we go along, is a worker role. And you can scale these up and down depending on your workload. So once you've got your TLE, next stage is obviously to validate it. There's a little checksum in there, and there's some other validation that you can do just to make sure that you've actually got the correct information. And all the TLEs are then turned into TLE objects and thrown into a queue. And this is where the real work starts. So you can take your TLE object off of the queue, and the first thing you need to do is to see, well, do I have it already? Because you might have got it from another source. So I have a TLE table at the bottom there, and that stores all of my TLEs ever. And I do a quick lookup in there to see if the TLE exists. If it does, I ignore it because I've processed it already. If it doesn't exist, I add it to the table, and then I add a notification to an update queue to let other workers know that, hey, look, I've updated this TLE, or I've got a new TLE. So a TLE basically is the position of this object now. But you want to know that your satellite's going to collide maybe in a few hours' time or in a few days' time. So you need to propagate this object. And for that, we're using a propagator. I've got 2 different propagators for this. There's SGB4, which is a fairly basic one. And we're also using a propagator that was developed in-house at Southampton. The propagator that was developed in-house in Southampton is about 25,000 lines of C with another 20-odd thousand lines of lookup tables. So it's quite substantial. And this is actually running up in the cloud now today. And to do that, we're using pinvoke, if anyone was interested in the technology there. So, so basically, calculate where is your object going to be in the future. And I have another big table here that basically stores future positions of objects. So now you have a list of all the TLEs, all the objects that you know about. You know where all these objects are going to be in the future. So the next thing to do is to take a look at this and see if any of these are going to have a conjunction, a collision. So there's another worker process that will come along and check for any conjunctions. And we're writing them to SQL Azure. Now, SQL Azure is the relational database. And all of this information here is accessible, well, either through the Azure API or it's all RESTable as well. So regardless of how, regardless of what you're wanting to do with it afterwards, all of this information is accessible in a standard format that's used in industry today. So I've got my TLE table and my propagation table, and I've got a list of conjunctions now. So the next thing is basically we can make that public, and people can download that and do their own analysis on it. To demonstrate how it works, I've got a client that I've written basically that will help visualize something. Now bear in mind, I did say these TLEs are published twice a day, and so today it was published at about 6 o'clock this morning, and hopefully that's all that processing there has been done this morning, and we're going to look at the most likely conjunctions, collisions, that are going to happen today now. So let me just switch over. You have to excuse the resolution, I'm afraid.
What's the definition of a conjunction? How close does it have to come to be a conjunction?
So when you look at an object, you're not really looking just at the object. It's more like a probability zone, so it's like an ellipse. If those two ellipses cross each other, then that's classed as a conjunction. Chances are they probably won't hit, but you don't really know where the object is inside that ellipse.
What are we talking about? Feet, miles, per
Feet.
satellite?
Feet, yeah.
And that's where the quality of the data is important, because you might find, oh, there's a possible conjunction. You might then go back to the satellite operators and say, can you give us more detailed information about where your satellite's going to be in order for us to refine that uncertainty?
Mm-hmm.
That's the scalable fidelity that the cloud solution can give you. So.
Yeah, because a TLE doesn't actually give you a very accurate position. So this was SpaceTrack that I mentioned that are publishing the catalogue. Here, just to prove that it is all running, and this is big, I am afraid. This is my worker processes here. This is the Azure portal. And now, here's for the show. So, I wanted to use Virtual Earth to display these orbits. And you can use the Virtual Earth API, but it's JavaScript, and by the time you start loading it up with many thousands and thousands of points, it's going to slow down. However, you can host Virtual Earth yourself. Now, because you can host it yourself, you can also host it inside a WPF application. WPF application is Windows Presentation Foundation, which is the next version of Windows Forms, effectively. Bear with me. So, the point is that now that I've got it into a WPF application, you can stream the application through the browser. So now I can stream Virtual Earth through the browser, and here's how it's going to work. It's called an XBAP. So when I click on this, and I'm doing this whilst the laptop's on battery through the wireless here, and it's an Azure demo, so here goes. It's going to it's downloading the application from Azure, and it's going to run it locally in a sandbox. And I think this is a key point here, that what's happening is, this is real software plus services. You have a thick client that's capable of using, let me just click activate, that's capable of using the local hardware, but it's augmented by services that are up in the cloud. And I think this sort of hybrid technology is where it's going to go. You're never going to say, look, move everything to the cloud, move everything locally. And to prove that it's, yeah, there we go. To prove that it's actually running on this machine here, if you look at the hardware acceleration on it, you'll see that it's very smooth. So here's the first example. Where is the International Space Station now? Well, it's on that line there. And this is an orbit that's been pulled off of my TLE propagation. So one of these lines, that's where it starts now, and the propagation takes it for about 12 hours into the future.
Is that configurable?
Yes. Yes, it is configurable. And just to show that it's all as you would expect, you can... Ooh, getting lost. You can zoom in and everything. So all the standard Virtual Earth features are available, and that'll up the resolution in a minute. There we go. So let me turn on some stars. Helps you with have a reference point. I think the most likely conjunction today hasn't come through yet, but I'm very sure the second one has, and there it is. So I'm going to turn off, the yellow one was the ISS, I'm going to turn that off just now. Ooh. There we go. So the red and the white lines are two different satellites, and you can see that if I hold it up to the edge, you can see that the two paths do cross each other. Good oats. I think all the rest look roughly the same. So here's another one. So the key point is, and I know this is a very simple client, and it's something I've done, but the fact that all the data is available in a standard format means that you can use it in other pieces of software, such as AGI's SDK, which is the sort of the industry standard software for doing conjunction and satellite tracking. One last thing I wanted to show, and that is the ability to basically look at your what's called the cloud drive. It's an example application that basically lets you look at your blob storage that's up in the cloud. And also, if I change to my queue drive, this will give you a list of all my queues that were used to support the application and giving you a message count in them, just to give you a feel that it is all actually up and running. And I think that's it. I'm going to hand back to Kenji, who's going to do a quick last summary.
So that was the, do you want to get it back to PowerPoint for me? Thanks.
The fact that the orbits come close to each other, I mean, what if they're 6 hours apart? Do you care?
No, not at all. The conjunction analysis is at a particular time, do they overlap? Or what time do they overlap? So,
you can't see that.
no, we can't see that in there yet. No, that's just, we haven't put that into the visualizer yet.
You don't want to fall into the mistake of trying to rewrite an entire application which the astronomers already are using, such as AGI's SDK.
Yeah.
It's an excellent piece of software. They've spent millions writing it, so you can't compete with that. The idea was just to show some cool technology and to just develop a very simple client to help you visualize what's actually going on underneath.
So that might be a simple client you do, and then you phone up your operator and say, so if you're on the road and you get a text and it says your satellite's going to collide, you think, uh-oh, go into an internet cafe, fire up the web app, go pff, and then you can phone up your operator who fires up the full software, and then over the cloud can pull it down on their machine with the full software to then talk to you over the phone, and you can say, okay, you need to do a maneuver in 3 hours. They do these spiral maneuvers to move the satellite. So it's that sort of ability. So what we're doing now is we're extending this platform. So we've got this kind of idea of the storage and the workers and all of these tools. And so what we're now doing is extending that for the NEO problem. And so what we need to do, where we've got the TLEs who want to do some NEO detection, talking to Alex about the Pan-STARRS projects, which are a very exciting digital telescope, and hopefully we can work with Alex to see if we can pull in the Pan-STARRS data into our Azure workflow here. Then we want to do trajectory modeling, so you need to, again, this is what was happening with Apophis. People were keeping updating their trajectory modeling. What's interesting there is actually looking at impact modeling. We have a global impact model that shows that if the asteroid hits off the west coast of the US, there are going to be this many casualties because we're going to get a tsunami, an earthquake, a blast wave. And so doing all of that modeling, but as you refine the trajectory, your impact point's going to change. So you then need to rerun your impact modeling code. So this is what we're putting in. And then there's deflection planning. So at the bottom right, you can see a gravity tractor spaceship that's being designed by Astrium. So if an asteroid is coming and it's going to hit, you might want to move it out of the way. Lots of people go, why don't we just nuke it? Two things. If you nuke it, you change the trajectory. It may be that it was going to land in the middle of the Pacific and it's now going to land in the middle of the east coast of the USA because you've accidentally deflected it wrong. And the other thing is if you blow up an asteroid, you get a shotgun effect. So rather than getting one big asteroid, you might get 100 50-meter asteroids. So you may just blow up more of a part of the continent. And the last thing is decision support. So this is where we actually want to help the decision makers, whether they're governments, okay? So one of the films they did on TV was trying to convince the US that the US should take the hit because there'd be fewer casualties if it landed in the Arizona desert than if it landed in Europe. So decision making can be at that level, okay? And so we want a tool that's up. So the US Air Force ran an exercise in December last year where they had the US Air Force, Department of Homeland Security, all the emergency services, local government, federal government, and they tried to do this, and they couldn't pull all the information together, look at it, and make decisions. And that was in December. So it's a big problem, actually, because, like I said, little or no warning that one of these things is going to hit. So we're not quite ready yet, and we're trying to get there. So just to wrap up, we looked at cloud computing. It's early days. This is the first time we've really written anything for the cloud, but we've decided, as always, to do quite an end-to-end application to solve a real problem. For this particular application, we think it's a pretty good fit. In terms of, we've looked at climate change in the oceans. What's the potential benefit to humanity for this? Well, we could save the planet, potentially. That's a good one. And we think it's a new paradigm for programming, really. And so we're pretty excited with this, and it's been a really good experience. So if you want to talk to us about it, then please do. So our email addresses are there. So thank you very much.
Thanks, Kenji. So when are you going to finish? You have until 2029?
2029, yeah. Yeah, it's going to take us that long to get the funding.
Any questions?
So the application that you're running on the cloud for the projection trajectory modeling, are you doing parallelization, and how many nodes are you using, and how much compute power is required?
Well, I don't have that many instances, so I'm a little bit stuck. I'm using 8 for that. But it's actually an embarrassingly parallel task, because all you're doing is propagating where is my object going to be in the future. You can do that for all 10,000 in parallel. It's then the conjunction that's the part that you can't do in parallel.
So we'd like more Azure compute time, please, to demonstrate the burst capability. But we're limited to the beta, basically, which was 8 workers. But we would like more worker nodes.
And then so for you get the update twice a day, you're doing a 12-hour projection. How long does it take you from the update until you have the data?
So not too long, about 3-4 hours, but that's not running on many nodes.
It's on 8 nodes.
Parallel,
It's embarrassingly scalable.
Yeah.
So
the chances
yeah.
are you don't want to just look at 12 hours. You want to be looking a week in advance. So, for example, like the Iridium one, they have to upload their satellite maneuvers 14 hours in advance. So, that's a problem. You're looking for a week would be very nice. You can't go much more than a week.
So we'd like to show the scalability of the application. It'd be nice to do that experiment.
I know that the code goes longer than a week because Hugh uses it for very long term, like 1 or 2 years. But the problem is the data you're putting in, TLAs are not very accurate.
So, how variable is the workload? I haven't understood why the cloud is better than just a dedicated server to doing this.
So there's 2 scenarios. Twice a day, I'm obviously hitting load, quite high load for 2 to 4 hours. The other thing is, imagine when there is a collision. The last collision, the Iridium one, produced an extra 2,000 objects. I'm only tracking 10,000 already, but that could have been a lot worse because all of those satellites in that constellation are in the same orbit, or the same altitude anyway. So the chances are you can get a snowball effect where we take out all of the satellites in that area. So potentially you're looking at hundreds of thousands of pieces of data of objects to track. The other thing is that those 10,000 objects that we're currently tracking, there's actually about 300,000 that we would like to track. So in the future, that's going to scale up.
So it's this burst capability. So like I say, it's when those TLAs are published, you want to be able to do the computation quickly. And then if you've got a conjunction you're worried about, you then want to just do the computation. And if your satellite is worth $300 or $400 million, you're willing to pay for that extra bit of compute. Whereas what you don't want is a warehouse of 5,000 machines sitting there doing nothing for 364 days except for that. So that's why this, and it's really important for the NEO scenario. So for the NEO, so in the event of a national emergency, the US government can commandeer airliners. They did it for the Iraq War. So here, the US government could commandeer a cloud data center and say, right, well, actually, we kind of want to calculate this, where this NEO is going to hit. And then suddenly, you've got a fixed amount of time when this thing's coming to the Earth, and you're wanting to do is, especially for the decision support and the impact. And so having that So actually for these scenarios, which are kind of what if, it might not happen, but when it does happen, we really need to respond quickly. So these emergency scenarios, this is quite an interesting infrastructure. So you can imagine for emergency services, again, for disaster response, so something like Hurricane Katrina, that type of thing, where you needed to model something very quickly. This is quite useful. So potentially for weather modeling, it could be quite interesting to be able to do that. So again, it's that's why we chose to use this, because like I said, I've got an 8,000 processor machine, but again, it's a utilization thing. So it's not necessarily good for any application, but for this application, it's the burst that.
One last question.
I have a question about monitoring of the application. Is a person have some problem with monitoring in that distributedly and remotely? So what if something application died, and how do you know that thing happened? Everything will have to begin start from the beginning?
No. So basically, every worker process, if it dies, the items will reappear back on the queue again, and so we'll start getting processed with the next worker that comes alive.
So I know that's assume default provided. So whether the user will know if something wrong in that process.
I do have an event that says that something has happened here, because I've rewritten the queues to make them basically so I know whether objects have been checked out or not checked out, where they've gone. So I can tell if something hasn't been updated, but the user doesn't get notified currently now.
Okay, so the same job probably can run 5 hours, but unluckily sometimes there will be 6 hours due to some failure.
Yes.
Okay. Another thing is, I often think about what if do you have the very big, huge data to transfer to the cloud?
No. So I mean, the catalog is probably only a few megabytes. By the time I expand it, it's gigabytes. It's very manageable.
Okay. That's not big.
Yeah, and the other thing here actually was we're keeping the data in the cloud. So we're not pulling the data back to the client. We're doing all the processing in the cloud. Yeah, so we don't have to pull that gigabyte of data down.
Well, thank you. Ken.
Thank you.
Thank you.